2 minutes. Hopefully. You never know. So it's always an exciting day as far as alarms are concerned. All right, it's 11. We're going to start. Hey, we're going to start. It's 11. Okay. Let's get going. Lord, thank you so much for bringing us together this morning. Thank you for everything that you do for us and all the blessings that you've given us. I pray that you would help us to stay focused, not just this week, but all of the rest of the weeks of the summer. Help us to keep our heads in the game. Help us to get our mindset right so that we are maximizing our success on the quiz that is coming on Thursday. In your name we pray. Amen. All right. We'll just keep going, right? Just keep going. So we're going to recap. We're going to talk about your water tower design project, both aspects of it, the design paper and the presentation. And then we're jumping into trusses today, right? And many of you are probably like, finally, trusses. I've been waiting for the equivalent of nearly 6 weeks to talk about trusses. And most of you are probably like, I don't even know what that is. And we'll find out. That'll be great. It's going to be awesome. Everybody loves trusses. So anyway, 3D moments. Yeah, they're a thing, right? It's a 3D moments. So we talked about this a little bit last class. I know it's confusing. The more that we see it, the more, I hope, the less mystic it becomes, I guess. So really, what is it? Well, a moment is just a measure of how much rotation or torque we have in a system around a certain point, right? Or an axis. And in this case, so we can treat it like a vector, right? And you'll see it drawn as an arrow sometimes that has a sweet rotation around it, and that'll signify that we have some sort of moment vector. And we can break that down into X, Y, and Z components just like we would any other vector, right? And I think you have to decouple that in your head, that a rotation doesn't have to be drawn as a rotation. It can be drawn as an arrow. Because if you just look at it as if it is another vector, what you have to do with it is really simple, right? The nice thing about a moment is that we define it as a vector cross product, right? So it's the distance we are away from whatever we want to know the torque around, cross the force vector, right, itself. And so what happens is we end up, because of that definition of using a cross product, we create a new vector that is 90 degrees to both of those original vectors, right? Which is the whole thing with a moment, right? It's the whole deal with it, that a moment has to be 90 degrees to both of the vectors that created it. And if both of those are at some weird angle in 3 dimensions, then you don't really get, you really don't get a good physical sense of how the system behaves, right? And so if you're trying to build an intuition on 3D moments, I would very much encourage you to draw these free body diagrams as planar 2-dimensional 3D diagrams and see how the moment behaves in each of those planes. Because that will give you a better sense of how it's supposed to, how it rotates, right? And it gives 2-dimensional, I think, is much more intuitive when we look at it, right? We have our object, we're pushing a force here. Okay, so that clearly causes a rotation this way, right? If we have a force that's pushing down at an angle, well, when you turn it, right, now you've got both of those components in this axis, and you can kind of see that this would cause a rotation kind of like that, right? And if this were wide enough and I was pushing at the edge, it would cause this sort of rotation, right? A spin as well, right? Depending on what field of engineering you go into, all different engineers have different names for the different types of rotations that happen on systems, right? Aerospace engineers call them roll, pitch, and yaw, right? If you have something that's going around the central axis of something else, mechanical engineers call that specifically a torque. Everything else is just a moment in a different direction. We don't really talk about torque. So, like, think about a bolt, right? How much torque do I need to close a bolt, right? That is specifically around the axis of rotation of the bolt. All the other stuff we call bending in mechanical engineering. It's a bending moment. Biomed, you guys take a little bit from mechanical when it comes to structures, right? And so you would probably call them torques and bending moments as well. And electricals, you guys don't do much with structures, but turns out that cross products are important for both magnetic fields and then understanding how, turns out that when you create an invisible force of a magnetic field, that might interact with other objects and cause issues, right? So we need to understand that as well, right? So moments aren't that big of a deal in electrical engineering, but you guys have your own other dark magic that you have to worry about. John Wick is on there. I haven't seen him, so I don't think he's in this class. Anyway, ball. It's ball is in 3 dimensions, is typically a sphere. Unless you're playing football, then it's more of an egg shape, I guess. I don't, why is ball on there? It's ball and socket joint? Yeah, there we go. Ball and socket joints. Okay, so 3D reactions, right? 3D reactions to connections, to joints. These are, again, we start with the 2D ones for a reason. They're a little bit easier for us to kind of grasp, right? So what does a 3D, what does a ball and socket joint allow, right? It allows rotation in about all 3 axes, right? It allows rotation, but you would, and I use the shoulder here because it's a ball and socket joint. My shoulder wants to keep my arm and my torso together, right? That is what it wants to do. You can force it to not do that, but that typically causes lots of problems, pain being one of the chief things among them. But that socket, that when I pull, if somebody were to pull, if I held my arm straight out, somebody were to pull my arm, right? My shoulder joint is going to resist being separated. That's the reaction force. If you were to try to push it up, pull it upward, right? you're going to resist being separated. If you try to pull it out, it's going to resist being separated. Those are my reaction forces, but I can rotate it pretty good in most directions. Now, you can't get full range of motion with this ball and socket joint because you have tendons and ligaments and muscles all in the way, holding it, constraining it to move in certain ways, right? But you can get pretty good, right? Okay, that's the idea of a ball and socket joint. So what are the reaction forces? The ways that we are resisting that motion. Reactions prevent motion, right? So in 2 dimensions, we talk about a pin, right? And a pin allows you to have a moment, right? We rotate around a pin, but we don't move left, right, or up and down at a pin, right? A pin holds us in place, but we can spin around it. Same idea for a ball and socket joint. It's the 3D version of the pin joint, okay? It's a 3D version of a pin. If you guys don't remember that, that's fine because table 5.2 exists in your textbook. And it takes 2 pages. And it actually tells you how many unknowns, and it tells you a little bit of a description about each one, right? So if you were to go to ball and socket, 3 unknowns, the reactions are 3 rectangular force components, right? It tells you very specifically in that table. I would recommend when you're doing your homework that you have the textbook open to table 5.2. It is in chapter 5, section 5. So 5.5, table 5.2. Fire alarms. Yeah, that was a thing. Certainly happened. Um, Everything was confusing. That one's going to need a special visit to my office. It's going to take a little bit more time than what we have here today. Trust. Okay, sure. Maybe trust. I don't know. Okay. Trig angles perpendicular. All right. Maybe that's 3 different things. We use trig to determine lengths of triangles that we don't know, right? Specifically in this class. And so that that's a nice way of saying we need to resolve our forces into their components, right? We're going to break things down into components. We're going to use trig to determine the legs of a triangle that we don't know. Thing about trig is if you don't have a triangle, you can't do trig. That's not entirely true, right? But it's mostly true. And in this case, we're not doing anything weird with like hyperbolic sines or cosines. We'll talk about cables a little bit in the next couple weeks, and then we can talk about hyperbolic sine and cosine and why that's evil, and whoever invented it, probably also invented other things like in the Middle Ages to torture people. But that's fine. The angle, the side of the triangle that's across from the perpendicular angle, like a right triangle, is the hypotenuse, right? That's our resultant vector. Okay. Not really sure where we're going at there, what we're looking for. Okay. Is there anything else on here that you guys, or that's not on here, that you need me to cover immediately right now, and we cannot move on past where we are? No, no. All right. In that case, we're going to do a thrust bearing problem. The rod here, this rod ADB, let's call it. You notice that it is bent. It's supported by a thrust bearing at A and a cable BC. And it is subjected to an 80-pound force pointing down at D. We want to find the reactions at the thrust bearing A and the cable BC. So we're looking for the reaction forces on this system. Right, so there's a couple of things that we're assuming when we're given this, right? First of all, we're assuming that since this is a statics class, we are in some sort of static equilibrium, right? So we want to know how do I have to balance these forces to determine that this will stay up with 80 pounds hanging on it, right? You can see our plan here. We're going to set up our XYZ axes. We're going to draw our FBD, write the forces using scalar equations, and apply scalar equations of equilibrium to solve for our unknown forces. Okay. First of all, we need to know and understand what a thrust bearing is. There are many types of bearings, right? There are journal bearings, single journal bearings. There's single journal bearings with a square shaft. There are single thrust bearings, right? There's a couple. And so what we're going to do is we're going to go to table 5.2 in our book, right? So I think a thrust bearing is not clearly named, right? Because here it's a thrust bearing. You are assuming that, well, at least I always assumed that you would be able to move the shaft through it, right? Because it's a thrust bearing. But that is not what it means. It is actually stopping thrust. So this is only allowed to spin around the y axis, right? And so if you go to table 5.2, a single thrust bearing has 5 unknowns. Right? And we'll draw the free body diagram in a second. The reactions are 3 forces and 2 couple moments. The couple moments are generally not applied if the body is supported elsewhere. We're going to apply them here and we're going to solve for them. Okay, so let's start with our free body diagram then. Oh, grab my pen. So I'll set up my coordinate axis. I don't really want to use red for that. I'll draw it here, and I'm going to draw it on the diagram as well, but never hurts to have it in multiple spots. Remember that the sense of our rotations go in this direction. That's the same as writing our IJK circle, right? Remember that from last week. I know it was a long time ago. Okay. So we've got our coordinate axes. Now let's draw our system. I'm gonna put point A right here. We're gonna come down in the Y. We'll have our curve. We'll call this point B, and we'll call this point D. Here's point A. C, X. And I realize my drawing doesn't really match the angle that this is at, but it's not really the point of having that. The reason I want to draw this on the diagram is because I want to show that my bar from A to the bend is lying directly on our y-axis, and that's going to be pretty important. We've got a couple of things here, right? We've got this cable. This cable is from B to C. Is it going to be in tension or in compression? Tension, always. Why? Because it's a cable, and it will always be in tension. It can never be in compression. Well, it can never be in compression. Okay. But what if, no, never. Answer is never, never be in compression. Okay, so if it's in tension, that means that it wants to pull this back up. And I'm going to call this, FBC, because that seems really simple to do that, right? Great. So we have FBC. And then we have this journal. Well, let's draw the reactions for our thrust bearing, not a journal bearing. So our thrust bearing. We look at the textbook, right? Textbook shows us that we've got 5 reactions on here, right? Okay, we know this is a 3D problem, so the maximum unknowns that we can be looking for is, it's 6. 6. Remember, you have 3 equations for force and 3 for moments. That's 6 equations, 6 unknowns. So if this were fully constrained at A, we would be over-constrained and we'd be statically indeterminate, so we can't do our analysis because we'd have more unknowns than we have equations, right? So in this case, we'll start with the forces, right? I've got this guy, AX, this guy, AY, and this guy, AZ. Maybe that wasn't the best color, but okay, great. And we have rotation. Now, a thrust bearing clearly does not allow us, it keeps us in place. It's going to allow our shaft, our rod to spin, right? And so if it allows spinning, it looks like if you go back to the original drawing, which we will do just to highlight this, you can clearly see that the shaft goes through here. So this should be allowed to spin around the y-axis, but we don't want this we don't want this thrust bearing to bend, right? Or bend around the x-axis, right? We don't want it to bend around the z, and we don't want it to bend around x, right? And so we're going to resist those motions, and typically down here, right? And that would keep it in place. So we're going to show this with I'm going to use a different color. We'll call it here MA in the z direction, around the z-axis, right? And notice I drew it positive, right? I drew it positive. Remember, I will draw everything positive. And this next one is going to be here. That's MA in the x direction. And I don't like how that looks, so I'm going to do that. MA in the x direction. It's also positive if you look at the YZ plane, right? Positive is this way, which is why I drew that up in the corner, because I want to keep my sense of positive there. Okay, there's one more force that's applied that we'll throw on here, and that's at point D. And this one's just called F. We're told what F is, but I'm going to leave it there for a second. And now we're going to do our dimensions, right? And so apparently we're just going to open up the Zoom menu first. It's fine. Maybe I could just do the thing though. Dear Microsoft, please and create better touchscreen technology. Regards, Dr. D. Hey, Bill. That's 6. So from the corner over to A, that's 6 feet. This is 1.5 feet here to here. And from D to B is also 1.5 feet. Okay. And there we have it, a complete free body diagram, right? First time seeing a thrust bearing. So we go to the textbook, we figure out what a thrust bearing does. Right? And we draw the picture. Cool. Let's write down what we know since we didn't do that yet. What are our knowns? Well, F, first and foremost, F is given as 80 pounds. That's, we got that. We've got some dimensions. But other than that, we're kind of on our own. And we count up our unknowns. We've got FBC, AY, AX, AZ, and 2 moments. We're at 6. Lucky us, that comes out to 6 equations, 6 unknowns. So what are we trying to find? I'm going to say that we're looking for AX, AY, AZ, moment about A at Z, the moment about A in the X direction, and FBC. Okay. So now you're like, man, am I going to have to solve 6 equations and 6 unknowns simultaneously? Maybe. I'm not going to tell you right up front where that's going to happen. Where's the fun in that for me? Um, so we'll start our analysis, right? So typically I like to start some of the forces in the x direction. You guys can start wherever you like, it doesn't really matter. But I am a creature of habit, and so if I sum my forces in the x direction, what forces do I have in the x direction? AX. Anything else? Okay, check. What about AY? Let's sum the forces in the y direction. Well, it's AY. What else? Anything else? Nope. Are those in tension or compression? Trick question, it doesn't matter, they're zero. Both simultaneously, tension and compression. The tension and the compression cancel each other out. And okay. Okay. Well, that's great. So now we've got four equations. So at most right now, what we're looking at is if nothing else falls out nicely, four equations, four unknowns, which is tedious, but not impossible. Six is a real pain in the butt, which is a technical term that we use. Okay, so let's keep going. If I sum the forces in the z direction, set that equal to zero, what do I have? Well, I've got a z. Okay, what else? Minus f plus f b c. All right. Well, in that case, I've got two unknowns in there, so I can't solve it directly, but that's all right. We'll just call this equation one, and we will move on. So now I've exhausted all of my force equations, so I have to look at my moment equations now, right? I'll look at my moment equations. All right. Which one do we want to start with? You guys want to start X, Y, or Z? X. All right. Start with X. Okay. Sum the moments about the x-axis. Where? Where? Where do you guys want to take the moment about? A? Let's say A. Why would you choose A? What forces go through the elbow? I mean, you can take it wherever you want, right? Like it doesn't really matter, but there is one choice that significantly reduces the amount of things that we need to track. So what makes a moment zero? What are the two conditions that a moment can be zero? One is that the force is zero. So it's not really helpful if but what's the other one? The distance is zero. So you ensure that the distance is zero for the most number of forces. Sorry, say that one more time, Ken. Yeah, you take the moment at the location where the most forces are applied. And that is point A, right? Point A's got three. And I know we just found that two of them are zero, but the other part of that is it again, it doesn't matter. You should get the same answer regardless of whether you do this at A, B, or D, right? Should. I did it at A. Okay. Why? Because when I look at my free body diagram, I'm like, oh, there's three forces there. I don't like that. All right. So if we do this about A, and I'll make a note here that was about A, because I don't want to write some of the moments about A in the X direction, because I named one of my applied moments moment about A in the X direction, and that is confusing, right? So we make a note. Okay, great. Some of the moments in the X direction. Okay, so what do we have? First off, we set it equal to 0. Then I've got to look at all my other forces. Well, first thing is first, I have a positive applied moment, right? So that just goes right into our equation. What's next? Well, we've got two other forces that we need to handle here, right? We've got F and FBC. Okay. So let's talk about F. Let's look at this picture. If I drew this in the YZ plane, this is what we're looking at, right? And if I push down here with F, right? Is that going to create a positive or a negative moment? Sorry, this is Y. There we go. Now we got it. Negative, right? It's going to go, it's going to want to push my bar in this direction. Okay, great. Negative F. How far away is that from A? It's 6 feet because we are specifically looking in the YZ plane for this, right? Right, and this is just me redrawing the FBD as it is, right? Okay, we handled F. What about FBC? Well, what do you guys think? What is the moment that is contributed by FBC about the x-axis? Exactly. Plus FBC times 6. As far as the YZ plane is concerned, these things are the same perpendicular distance away from point A. They're just stacked. You know, if we wanted to draw them both, they would look like this. And there were, but that's not as clear. So did them one at a time. Okay, cool. So we've got this. Again, we've got two unknowns here. So we're going to have to keep that. We'll just keep going. Call it equation 2. Plug things in later. All right. Let's take the y direction moment. If I sum the moment about the y-axis, I should have, well, there's no MAY, right? We don't have an applied moment in the y. So we just have to deal with F and FBC. And it's specifically around the y-axis. So if I were to draw the XZ plane, right, and we want to handle F, oh, and we're done. Just trying to write feet. Take it easy, pen. All right, so that's 1.5 feet away. Is that going to be a positive or a negative moment? It's negative, right? Because look up here, xz, z into x, right? Z into x is our counterclockwise, right? So this would cause a clockwise rotation. So yeah, negative F times 1.5 feet. I can do the same thing with FBC. This distance is also an additional 1.5 feet. And so what's the moment contributed from the tension in the cable around the y-axis? That plus FBC times 3. Well, this is very interesting because I only have one unknown in this equation. So I'm going to solve it right now, right? Because 3 times FBC is going to be equal to 1.5 times the force that's applied. And so FBC should be 1.5 times 80, which is the value for F that we were given, divided by 3, which comes out to 40 pounds. And it's positive, so we know it's in tension like we drew it. So if you'd drawn it in compression, if you'd drawn it pointing down, you would have gotten a negative answer, and you would have been told that that's not correct. So now we've got those forces. Well, that's nice because now if we look at equation 2, I've got a value for FBC and I've got a value for F. So I can solve for the x direction moment right now. So let's go ahead and do that since we're here. And I'm going to erase this guy for a second. Well, not for a second. I'm going to erase him forever. Sounds so ominous, though. All right, so if I'm going to solve equation 2 for MAX, right? MAX is equal to 6 times F minus 6 times FBC, right? Let's flip them. So that's 6 times 80 minus 6 times 40. MAX comes out to, that was not a good spot to write that. It's going to run into the other thing. So MAX is equal to 240 foot-pounds. And it came out positive, which means that the initial way that we drew it was correct. So we will go ahead and say, hey, that is counterclockwise. And for this, right, I'm just going to put a T here to indicate that that's intention. That'll be important later today. Okay, so the only other thing we have left is MAZ, and we only have one equation left, which is some of the moments about the z-axis. This one's pretty, so I'm gonna have to clear some room here. So I'll take my force equations out for a second. Sum the moments in the z is equal to 0. Okay, about the z-axis. So if we're going to take this whole thing and rotate it around the z-axis, right? So spin it like a turntable. Okay. Well, first of all, I've got MA in the z direction, or about the z-axis, right? Okay, all of the forces at A don't do anything. What about F and FBC? Do they contribute a moment about the z-axis? Let's ask it this way. Let's ask it this way. Let's use a visual. In this case, I know this doesn't have a bend in it, okay? If I apply a force at the end, what direction does this bend in? It goes this way. It does not go this way. What would it take for me to go this way? Some force that's angled in that direction, right? These forces run completely parallel to the z-axis. They are not perpendicular to the z-axis in any way. And so the perpendicular distance between the z-axis and these forces is 0, right? So this moment is 0 for this loading condition. It's not always 0. If I had applied a force at some angle, right, instead of straight down, then we need to deal with that. But then you're also going to have an x component or a y component of that force too, right? Okay. And that's it. You did it. We found the reaction forces. The setup is really important here. We need to understand what a thrust bearing is built to do, right? Look it up in your table. On the next quiz, that'll be included as part of the tables will be included. Because I don't think again, it's going to be one of those things where, you start to see them enough, you'll start to remember them, but I'm not expecting you I'd rather you use your brain space for something important, not memorizing a table that's readily available, frankly. But again, you can always suss it out, right, by trying to figure out how it's supposed to move. Questions about this? Questions. AZ was 40 pounds. That's what I got. Did we not solve AZ? No? All right. Let's go back and solve AZ. I got ahead of myself. So to solve AZ, what do we need? We need to use the sum of the forces in the Z, right? Sum of the forces in the Z equal to 0 was AZ minus F plus FBC. We know F, we know FBC. AZ is equal to F minus FBC is 80 minus 40, which is 40 pounds. Thanks, Cole. Okay. Any other questions? So we didn't have to do any simultaneous solving of equations in this one, right? We were able to kind of, once we wrote them, so I would suggest order of operations. Don't necessarily do it the way that we did it here. Write down all the equations first, look to see what you have, solve the easy ones, then go back and do substitution if you need to. That's what I would suggest. But you guys work how you work. I'm not going to micromanage your style or how you solve problems. That's not the point. Okay. Anything else? Anything else? Anything else? All right. Once, twice, lost forever until you go to YouTube. Okay. Quiz on Thursday. Definitely come to class for that. Homework on Sunday. Another homework week after that. Quiz 2 on the 5th. Homework 5 on the 12th. We're almost in June. That's pretty crazy. And then the CLC stuff that we are going to talk about, right? Yeah. Maybe. There we go. Okay. Oh, go first. All right. It's quiz week. Biggest thing about taking quiz and exams is your mindset. You have to walk into it feeling confident, right? If you think that you're not going to do well, it is a self-fulfilling prophecy. You will not do well. Full stop. No athlete, whether it is my son's under 10 soccer team or an Olympic athlete, walks in to a competition and says, you know what, I am entertaining the idea that I might lose this today, right? Why? Because it's not a productive thought. You walk into the exam, you walk into the quiz, you say, I'm here to do business, and I'm very good at business. Okay. Confident. Neil deGrasse Tyson says the key is to know enough about a subject to know that you're right, but not enough to know that you're wrong. Okay. So there you go. Okay. Be confident. Confidence. All right. All right. So water tower design. This is a CLC assignment. Please, by the end, we'll get to there in a second. So, allow students to perform design and analysis of a water tower. In doing so, you will investigate physical and economic constraints that accompany the design process. You'll come up with a design for 2 different water tower structures. So you need to do 2 water towers that are different. They can't, not 2 that are the same, 2 that are different. Okay. Each structure must be trussed and be able to handle horizontal and vertical loadings, and the design must also include the tank. So it's not that you're just designing the truss, you actually have to attach the tank to it, because that's the whole point of the water tower, is to store the water in the tank and make sure that it doesn't fall down. Okay, there is a full printout, a full Word doc on everything that is expected. We will go over it here, but it is in Halo, right? So when you open up this assignment, there's an attachment at the bottom. Click the link. It opens up the Word doc. It gives you all of the design specs that you need to hit in case you don't remember. Again, this is a written assignment, a group written assignment. You're going to turn in a paper at the end of this, right? So again, APA not required, but solid academic writing is expected. We went over this with the last paper. Cite your sources, right? Write professionally. If it sounds like a text message, it's probably not okay. And by probably, I mean it's definitely not okay. I have received, not in this class, but in the past, I have received emails and messages from students that have absolutely no punctuation and are just one long sentence. Don't do that either. I know that depending generationally, some people believe that punctuation indicates some sort of emotion. That is not true. It is just ways for you to stop your sentences from being one long sentence. Also, don't all caps me and don't use exclamation points unless you absolutely mean it. Okay. Or you're talking about factorials. It uses a rubric. Go through the rubric, and you have to submit it to LopesWrite. So what are we doing? Here's your design specs. You have your 2 different water tower structures. There's a few different aspects. First, the design specs, right? So these are the things that have to be common through everybody's, like the tank. The tank should be not the design of the tank or the shape of it, but the fact that you need to hold you need to be able to have enough water for 200 people who need half a gallon of water per day. This informs you to how much water the tank needs to hold, which will inform you to the weight of the tank when the water is inside of it. Also, you need to have a wall thickness of 1/2 inch in order, and you have to have the necessary volume to store the water needed. Obviously, because if you can't store enough water for everybody, then kind of didn't do the thing. All right. It must be made from readily available materials in case repair is needed. So I haven't gotten to a lot of the product plans yet. I will have them all graded by Sunday because you turned them in on Sunday. But for the most part, right, when you have a remote region, it's harder for you to get supplies in, right? And so we need to have things that we're making this out of readily available materials. Interesting side note, this summer, the engineer has gone global. Went to Costa Rica, and they did some work where they actually built a water tower for a small village and sent, Professor Collins was with them and sent me and Professor Tomford the pictures of them building the water tower and how, according to Professor Collins, everybody was super excited to actually use statics to actually do something. So there you go. All right. Yes. Yeah. Yeah. Awesome. It's really, I mean, it's great, right? It's a real world application, and it's going to help a lot of people. So so your water tower can't be open air. And so you're going to store filtered water there. It's got to have a top on it. The truss itself must be made of readily available materials in case repair is needed, right? These are not things that are going to affect necessarily your hand calcs, right? Or your design, your analysis, but they are going to affect the later portion of the project that I'm going to talk about. Your total system cannot exceed 130 feet in height and must not exceed 45 feet in width. So you have a total footprint of what this has to fit into. Okay. SolidWorks simulation. So part of this is you're going to create your water towers in SolidWorks and you're going to simulate them, right? So students will simulate water tower to determine the three-dimensional deflection of the structure as measured from the center of gravity of the tank at half and full capacity when no wind is blowing. So you have 4 simulations that you need to complete there, right? Half capacity, no wind for A and B, and full capacity, no wind for A and B. David. We will talk about it later, but not today. Okay. And I'll post some videos in the announcements too, so you guys have some good resources for how to do that. Okay. Students will simulate water tower to determine the three-dimensional deflection of the structure when the wind is blowing. Okay, so this one gets a little bit more complicated because there's 8 more sims that you have to run. So you'll see, okay, anyway. So average wind, so you need to do a little research, find out what the average wind speeds are for the region that you are deploying this in, right? Why are we doing this? Because we want to make sure that it doesn't fall down if the wind blows. That's really it. That's the thing. Okay, great. Hand calculations. So there have to be hand calculations as well. So you're going to do the simulations and you're also going to do hand calcs, right, for the wind speed. So you're going to repeat 8, you're going to do these 8 simulations and you're going to do the hand calcs associated with these, right? Okay. And then you're going to compare your hand calculations to what the simulation tells you and report a % error between the two. Okay. Now, which one should you take to be the true value, quote unquote? Well, it says the % error between the hand calc and the simulation. So I would probably use the simulation as the true result. But if you find that it's super off, you do need to investigate. Did I set up my simulation wrong, or is this a function that I messed up my hand calcs, right? So you got to figure out root cause for that. We'll talk about the rubric later, not today, but that is all in there. Okay. Good. All right, other considerations, design selection. So why are we doing 2 designs? Because the purpose of your design paper is to compare and contrast your 2 designs and figure out which one you are actually would recommend, right? So you need to make a recommendation based on your simulations, your hand calcs, right? You need a detailed production style drawing. Please, one of the biggest issues, not issues, but one of the things that ends up happening is students just give me a screenshot from SolidWorks of a 3-dimensional object. That is not a production drawing, right? If you took that to a machine shop, they would look at you and tell you to go home. I want the actual drawing of it, what it's supposed, like with dimensions and everything. Bill of materials. This is where your materials come in. You need a materials list and a cost, right? Because there is an economic part that goes into this, and this is what's going to drive it, right? So remember, they should be readily available materials, right, in case things break. Should include not just raw materials, but any tools for installation and repair. and hopefully, well, and then you also need to include assembly instructions. So how are you gonna tell these people, you can't just drop it off and say, figure it out. Are you gonna give them an IKEA book with the stick figure, putting it together, right? What are we doing here? They need something. They need something. You pull up your iPad, right, and you get the Lego app, and it shows you step-by-step instructions on how to build the Lego, right? I don't know. You guys need, you need to provide some form of instruction for how to assemble. Okay. Any questions so far on these? Yeah, Jordan. Yeah. Mhm. That is a great question that is not necessarily discussed in this design. We are kind of assuming that the water is going to be there. But that is something that hopefully you did take into account when you had your region of deployment, right? Because if it's too far, you're going to have issues with getting water to the water tower, right? And so when you guys meet as a group and you decide which person's product plan you're going to go with, that would be a great thing to talk about, right? I mean, it's up to you guys. Sure, it's up to you guys. That is a design decision. Ref. Mhm. Wait, say that one more time. I'm sorry. Yeah. Okay. So the way that it's written in the project description is that you're going to have filtered water coming in, right? So if you're going to put a filter on top of that, that's fine, but then you have to account for the additional weight of having the filter there as well. Yeah, Sam. Yeah. Mhm. Yeah, use SolidWorks to draw, right? If you have specific members for the trust that you need to create, then you can, typical practice would be like in the comment block, you would say, I need 700 of these or however many it is that you have, right? I will also point out that this is a very open-ended project on purpose, okay? There's a lot of stuff that you guys are going to have to make decisions about in the design, right? That you have to justify. So how do you justify it? Facts and data, right? Okay. The presentation. So that's the project. That's going to be a paper. You guys turn that in. There's also a presentation portion to this. Now, normally, well, not normally, this class is big, right? And if I have 10 groups and each of you have 10 to 15 minutes to present, that's the whole last week of class and what last week and a half of class, basically to present projects. And so we're not going to do that. We're going to make a YouTube video of us presenting our projects. Okay. So you have 10 to 15 minutes. The first half of the presentation describes clearly the problem that affects the population that you do not have a safe source of drinking water. Discuss how your design of the project relates to Christian worldview of caring and serving for others. Bless you. Second half is fully detailed description of your design and the selection process that you underwent to go from two designs to one design. Okay. Submit your PowerPoint presentation in the digital classroom, annotate each slide with your notes, right? That's just good practice. If you don't want to use PowerPoint and you want to use Google Slides, fine, that's fine. Equivalent, right? Remember, Halo only takes certain file types, right? And certain file sizes. So I've noticed this in the past. Sometimes students like to embed a lot of videos in their presentation. If you do that, Halo is going to yell at you because your file is going to be way too big. Okay. So I would recommend not doing that. What I would recommend is using a PowerPoint. You guys can choose whether or not you want to be on the video or you want to just talk to your slides in a video, right? You can use your favorite screen capture software or whatnot. but you got to put it on YouTube. You can mark it as unlisted, just don't mark it as private, right? Because if it's private, then nobody can see it except you, okay? And we'll talk about doing that in a second, right? This is all the standard stuff, right? So submit it using YouTube. Very specifically and clearly, what I want is you to create a PowerPoint file or a Google slide and film your group presenting, right? Using a webcam or a phone or screen capture or OBS or whatever it is that you are familiar with and are wanting to use. Loom, right? People use Loom too. Upload it to YouTube, send the link to someone else before you submit it to make sure that it actually works the way that you want it to work. Because if it doesn't, here's the thing about these presentations. If I can't watch the presentation, then I can't grade the presentation. So, right, please make sure your link works. Once you're done, put the link onto the front slide of your PowerPoint and then submit that as a file to Halo. And then I will click on the link and I will have the slides and it will be all good. Okay. Questions about this? Jim? Yes, correct. 100%. Turn it into the presentation assignment for sure. Okay. It will be viewed as not 100% if you just put a link or I just get a PowerPoint. I will grade as much as I can with either, but know that if I don't get both, even if it's the greatest presentation in the entire world, it's not going to get all of the points. Okay. Yep. That is what I'm saying. 100%. Sometimes people like to get they're like, well, Halo wouldn't let me upload it because it's too big, and when I zipped it, it was still too big, and so I gave you permission on my OneDrive, except that I really didn't give you permission on my OneDrive, and class is over, and I'm trying to get in touch with you, and then it's like a week after class is over, and I end up not being able to see your presentation. Please try not, don't, I'm just trying to caution you against some things that I have seen in the past that have not worked. But you know what always works is if you upload it to YouTube and you give me the link and you leave it as unlisted or public. That always works. Always. Okay. Fantastic. So here's what I need from you. By the end of today, I need one person from each of your groups to fill out the discussion forum post that I posted on Sunday night. And I list all of the people who are in your group, including yourself, just for completeness. And then I will have it. And if you didn't do it, then I'm just going to assign you to randomly work with other people. And that'll be that. Maximum of 4. Maximum of 4. Now, the thing about this that's awesome is that everybody will be able to see who's in which groups, right? And so there should hopefully be nobody. Well, hopefully you guys talk to each other and okayed who's going to be in your group first, and you just didn't put like 4 people's names down. That's what I would suggest that, right, is actually talking to each other. These groups, so let's say this as nicely as possible. If you decided that it wasn't worth your time to fill out who your group is, then it is also not worth my time to negotiate with you to get you into a different group. Okay? So there you have it. Not to be mean, but kind of a little bit. Anyway. All right. Questions about this? I'm sure. Look, the reason why we were talking about this today is because this is due like the last Sunday or the week before the last week of the semester. So I want to give you guys enough run up to be able to start it early and ask questions as you go. Please, please, please do not wait until the last week before this is due to start this project. There is a lot of work that needs to get done to complete this. Full stop. Okay? If you are waiting till the last minute, what are you ensuring? You are ensuring that SolidWorks decides it's not going to work for you. You are ensuring that, oh no, my charger doesn't work on my computer now, and I only have 2 hours of battery life until this thing goes, right? I would also recommend using shared files to do this. If you are going to say, well, no, Tyler has all of the files from my team, and Tyler's computer just dies the night before it's due, right? Sorry guys. Oh well, no, use either Google or OneDrive, use something where it's shared so that everybody has access to it. And also talk to each other and know who's going to upload the assignments when they are due, okay? Don't just trust that someone else is going to do it. No, know who is assigned to upload the assignments, please, okay? Okay. At this point, we haven't learned anything about trusses or anything like that, but that's going to change in a minute. Yeah, you need to trust your teammates. Oh, he did it. I can't believe he did it. Okay. Any other questions before we dig into some trusses? What? Sorry. Sorry, can you say that one more time? This is a spool? A spoon? Oh. No, not that I'm aware of. Probably the union. All right, here. We talked about this. Start it as soon as you can. I will post the PDF for the new version of SolidWorks, and you probably already have the 25 one, but if you don't, you can get it, right? I'll post it in the announcements later today. Follow the instructions. If you are going to uninstall SolidWorks from your computer and install the new one, make sure that you uninstall the old one completely. Otherwise, it's going to cause problems. Okay? It's going to cause problems. I mean, I don't know. I don't really trust wizards. Uh, um,
Well, we're gonna be taking our quiz Thursday.
yeah, exactly. All right. Yeah, what's up? Yeah, it didn't happen. Sorry. No, but that's why we're doing the review today. This be fun. So if I were going to post problems, how I would do it is I would go to chapter 2 in the textbook and I would pick like a bunch of problems at random. And then I would just put them in a PowerPoint slide for you guys. Like that's what I would do. No. Let's talk about trusses. Why should I care? Okay. It's a great question. Why should you care? You're in a business right now. That's why you should care about trusses. Trusses are ways for us to support things typically seen in roofs. You will also see them in bridges, right? It's a system by which we can transmit force from one point to another. Typically, think of it like a skeleton, right? It's the skeleton of a building. You apply a force at the roof and it drives it down to the footings, right? It's through one of these various pathways here, right? So things we want to know is how to determine forces in the truss members to be able to select their sizes, right? Again, we want to know how much force is being transmitted through our truss so that we can make a determination on material and size later. We're not going to talk about how to do that in this class, but you will in MEE 352. Again, a more challenging question is that for a giving load, how can we design trusses geometry to minimize our cost, right? And that again goes back to materials and things of that nature, right? Trusses are also used in a variety of structures like cranes, you know, frames of aircraft. The human body is technically a truss. Your skeleton is a truss, right? How can you design a lightweight structure satisfying load safety cost specifications that is simple to manufacture and allows easy inspection over its lifetime. I look like a civil engineer to you? I don't know. Jeez. It's a lot of stuff. Why would you hit me with that on a Tuesday afternoon? I mean, come on. I mean, there's a lot that goes into this, right? And it starts with us understanding for different loadings, what does that look like? Most of the time when you design like a bridge or building, you understand what the typical loading you're expecting is, and you design to that, right? There are certain cases where things arise that we didn't expect. You probably know about the Tacoma Narrows Bridge, right, which is a huge frequency response problem. If you don't know about it, check it out. The dog does make it to safety, so it's fine. But that's one where the bridge started vibrating and it wasn't supported correctly, and it was vibrating near its natural frequency, and so it starts to amplify the oscillations, and it looks basically like this bridge is a slinky at that point, and then you know, it's not good. Side note, if you ever decide to get your professional engineer's license, if you were the one that stamped the drawings for the Tacoma Narrows Bridge, that makes you legally responsible for its failure. So there you go. Yay, yay. All right, simple trusses. Great. It's a truss. So a truss is a structure composed of slender members joined together at their endpoints. Specifically, a truss is joined together. It's two force members that are all joined together, which simplifies it even more. Because if you see a three force member, it is not a truss, it becomes a frame. And we'll talk about the difference later. Okay, how do we do it? Well, we kind of treat it like a two-dimensional problem. Okay. So why do we spend so much time doing 3D stuff? Well, that's important too. We'll talk about 3D trusses later, but most of the time we can do it as a 2D problem. So you're like, well, this wind tunnel, you told us that we need to have wind blowing on it. How is that? Isn't that a three-dimensional loading? Is it? Think about it. You tell me later. Okay, roof truss. Named very creatively because it has this, it's for a roof, right? Not to be confused with a bridge truss, which would look pretty much the same as this, but on a bridge. This is a purlin truss. You can see it does have three-dimensional behavior. Notice that there's no cross beams going across the entirety of the truss, right? We're not expecting high loading from the sides. We're expecting high loading from the top, right? Okay. A simple truss is a planar truss, which begins with a triangular element like this one. And then we expand it by adding two more members in a joint like these guys here, right? And so the number of members, M, and the number of joints are related by this equation. So the number of members is equal to 2 times the number of joints minus 3. So if I have 2 joints, I only have 1 member, it's not a truss. It's not. All right, so look, this has 3, right? This has 3 joints. 6, 3 members. Okay. Is that super important? Not really. Not really for understanding how to analyze trusses or how force is distributed through a truss. But if you were going to be making a truss, right, you would need to know how many joints you would need for the number of members you have, or vice versa. Okay. Okay, analysis and design assumptions. When designing the members and joints of a truss, first it is necessary to determine the forces in each truss member. Force analysis. So we do a force analysis. 2 assumptions are: first, all loads are applied at the joints, and the weight of the truss member is neglected. That's actually 2 assumptions in the first assumption, right? So we're going to neglect the weight of the member, right? And then the second or third assumption, depending on how you're counting, is that the members are joined together by smooth pins. Why is that important? Because we don't have to deal with friction in the pins. If there's any rotation, it just is allowed to freely rotate about that point. Okay. All right. Again, this allows us to say that all trusses are made of two force members, individual two force members. How many forces do we have on a two force member? Everybody together. How many forces on a two force member? Hey, thanks, Ken. It's two. It's in the name. All right. So they're either in tension or compression. Often compressive members are made thicker to prevent buckling, right? But that's something we're not going to talk about in this class. Notice that if I am pulling in tension, that means that the pins are going to be a reaction force to that tension. Okay. All right. Let's take a minute. We're going to take a 2-minute break. 2-minute break, and then we'll come back.
And like, don't forget.
Mm-hmm.
When we design the tower, we need to say like it's made out of wood, metal, like the material side of it.
So it shouldn't affect what we're trying to do in the analysis. Because so think about when you do your comparison to hand calculations, what are the factors that are driving the difference between what SolidWorks says and what you did, right? So yeah.
Professor Ross was saying.
She said no. Yes. Let's talk about after class. Okay. Well, she's
Spanish at
yeah.
30.
Yeah, she said typically so All right. We're back. Maybe. Let's see. All right. We're back. Method of joints. What's that? That sounds fun. Let's do that for sure. All right. So how do we do our force analysis on a truss? There's a couple of different ways. We're going to start with one called method of joints. Essentially, each of our joints is a pin, right? And so what this is going to require us to do is a couple of things. First, we draw a free body diagram of the entire system. And then essentially what we're going to do is we're going to explode our truss and we are going to analyze all of the forces at each one of our joints and solve the things that we don't know. Okay? Cool. So in this case, right, I would first get my reactions at A and C, and then I would have to determine, I would draw my free body diagram for each of my joints and figure out what my unknowns are, right? So in this case, right, we know we can start here because we have two unknowns coming out of B, right? And so it's a 2D problem, two equations, two unknowns. We don't deal with moments in these types of analyses when we're talking about method of joints. It's just force equations. So here's the steps. One, FBD for the entire system. Why? Allows us to find the reactions and allows us to get global perspective of what the system is doing. Okay. Two, FBD of a joint. Which joint? Doesn't really matter. You can pick whatever joint that you want to start with. I would recommend looking for joints where you have only two unknowns and then starting there. And then you just use some of the forces X, some of the forces Y to solve your unknown forces, solve for your unknowns, move to the next one, right? Rinse and repeat until you have all the forces that you need or want, okay? Pretty straightforward. If you're doing like a large scale truss, right? You know, maybe you write a MATLAB script to help you run through it. I don't know. You can figure that out. But it's pretty straightforward and you just you rinse and repeat until you're done, right? Great. Let's do one. This is a truss. It's cool. Looks good. It's being loaded at point D with 450 pounds. We want to determine the forces in each of the members of the truss, and we want the reactions. It doesn't say that, but we're going to do it anyway. Okay. Well, this is a pretty sweet truss. What kind of connections do I have at the base? Roller and a pin, which gives us three unknowns, which is good because overall, when we're not looking at the pins, this is a 2D problem. So we have three equations and three unknowns in 2D. Why don't we use moments for method of joints? What do you guys think? Moments come into play here, but not for method of joints. Why? What happens if I take the moment about the joint that I drew the FBD for? They're all canceled. All the forces pass through that point. So it's just going to tell you that some of the moments is zero because there's no moments, which is, as my old controls professor in undergrad would say, is trivial. It's a trivial solution. All right, anyway, let's draw the free body diagram for the whole system. I've got point A, point D, point C, and point B. B, C, D, okay. I've got some forces. I've got this force here, which is 450 pounds. I've got a roller down here. We know that a roller only has a normal force. And I've got this pin over here that I will cleverly call CY and CX. And I will put on my units in a second, my dimensions. This is 4 feet from top to bottom. Four feet. That's also 4 feet from each of the other sections. So here's a question for you, for all you trigonometry experts out there. If I'm looking at this set of two right triangles, what's the angle between AB and AD? 45 degrees, right? 45 degrees. So we know that angle. I'm not going to write it down, but I've given enough information that I know what that angle is just by looking at it. Okay, so if we're going to do this part, I'm going to need more room. Move my FBD up here. Okay, so we're going to get the reactions first. Reactions are going to be, well, we'll sum the forces in the x direction. Or, try that again. Sum the forces in the x direction, set it equal to 0. That's negative 450 plus CX. So look at that. Right away, we were told that CX is 450 pounds. That's great. And that makes sense if we're looking at it, right? Because if I'm pushing at this on this thing completely in the x direction, then that x direction force has to balance it, right? Has to. All right, what about AY and CY? Well, the sum of the forces in the y isn't really going to help us. It's just going to tell us that AY is equal to negative CY, right? So we need a third equation. I'm going to sum the moment at C, set it equal to 0. And if I do that, well, I've got 450 times 4. That's a positive moment. Minus AY times 8. That would be, as I've drawn it, that would be a negative moment, right? So we can solve for AY, right? $450 times 4 divided by 8, or 450 times 1/2. £225, which means that CY is a negative 225 pounds. Now, this also makes sense that they would be balanced, right? Because there's only two forces and they're equidistant apart. And so they would each reflect each other, right? But think about what's happening globally. If you push at the top, that wants to push everything in this direction, right? A couple of forces, well, that's that, I suppose. Oh, come on. Not, there we go. A couple of forces here, where this one's up and this one down, creates a rotation that counters that, right? So that's what's going on from a global perspective. All right, so we've got our reactions, CX, CY, and AY. Perfect. Now what do we have to do? Well, we were asked to find the force in all the members. So just to remind us, we want to find AY, CY, CX, FAB, FBC, FCD, and FAD. Force in all of those joints, right? All those members. So where are we going to start? Well, like I said, we can start wherever we want. If I pick point D, is that a good place to start? Well, let's draw the FBD for joint D. And I have this force going this way. and I've got FDA, FTB, and FDC. Three unknowns. I have two equations. It's not going to work out for me. Joint D is not a great place for us to start. We're going to hold that FBD and we'll move to a different spot. Okay. Similarly, if I look at joint B, I've got three forces here. Probably not the best place to start. So I want to start at either joint C or joint A, right? Joint C or joint A. Let's start at joint C, right? So again, FBD for joint C. Now, the nice thing about these is that you are going to notice that you don't need to solve all of them, all of the joints to get the answers that you need, right? So you're going to have a couple left over or one left over. You can use that one to check to make sure that you're getting the right answers so you can have confidence in what you're doing. So we say that this is CX, this is CY. Remember, we found out that CY was negative, and so in subsequent FBDs, we will draw it in the correct direction. I'm assuming everything is in tension to start. Okay. So we can write this out, right? So I've got two equations, sum the forces in the X equal to 0 is equal to CX minus FCB minus FCD cosine of 45 degrees, because you guys told me that this angle is 45 degrees. And because I know that it's 45 degrees because of the geometry that was given. Sum the forces in the y direction. You get negative CY minus FCD sine 45 degrees. Well, we should be able to solve that second one right away for FCD, right? FCD is equal to negative CY divided by sine of 45 degrees. CY we found was 225, right? So that is 318. Hold on. Which one are we looking at? CD, right? Yeah. Sorry, that should be plus. What am I doing? That's pointing up, right? CD is up and to the left. So that should be positive. That's what was throwing me off there. Sorry, apologize. So the directionality of these depends on our coordinate system, right? So if we do this, that's 318.2 pounds. And guess what? We assume that it's in tension, and because it came out positive, it remains in tension. Okay, great. Plug that in for FCD in the top, in the first equation. Solve for CX. Sorry, solve for FCB. Why am I solving for CX? FCB is equal to CX minus FCD cosine 45 degrees. We found CX was 450 pounds. Right. You guys see that? Kind of move it in a second. So FCB gives us 450 Guess what 318.2 times cosine of 45 is? It's 225. So this comes out to 225 pounds, also in tension. And this is now, for trusses, this becomes important for us to determine whether or not we have tension or compression. So the typical convention that you will see is that people assume tension, and then when it comes, if it comes out negative, you tell us it's in compression, okay? And that's fine. Some people like to do it the opposite way, also fine. But if it comes out negative and you assume that it's in compression, then it has to be in tension, okay? So just make sure that you are tracking that, because there are certain problems that you have in the homework that ask you specifically, what's the force in the member and is it in tension or compression, right? Okay. So we solved joint C. Great. I am going to keep some of this and remove the rest. I'll put my forces, we'll put the forces that we found up here. Where should we go next after joint C? What do you guys think? Joint A? We could sure do that if we wanted. Doesn't matter, but notice what something that we did, right, is we eliminated, we now know this, right? FDC is FCD, they're the same, equal and oppositely directed. So now we could move up to D if we wanted, and we could solve that. The way that I did it was I moved to B next. Again, doesn't really matter. You just want to make sure that you're going to different joints that have two unknowns as opposed to three. So I'll get rid of this stuff now. I'm going to leave joint D there because we'll end up there eventually. But I want to show you something interesting that happens at joint B. So if I'm at joint B, I've got forces that occur this way, FBD and FBC and FBA. Okay. Everything, we keep it in tension because so far we haven't found anything in compression, right? So everything stays in tension. FBC, we found that earlier. It's FCB, right? It's 225 pounds in tension. Okay, well, let's start here. I'm going to sum the forces in the Y just to change it up. I've got FBD. Do I have any other forces in the Y direction here? This is zero. There's no force in this configuration. There's no force that is being carried through here. This is the idea of a zero force member. And we'll talk about it in a second, right? But that's really helpful, right? Because you could have, if you were to inspect this and say, I know that that's a zero force member, then you can just go right to D and figure those two things out. And then you only really need to do two of the links, right? All right. So anyway, doing the full complete thing, we also find out that FBC minus FBA, and so FBA equals FBC. So I'm just going to come up here and write equals FBA and call it a day. Also in tension, right? Because it comes out positive. If I were to plug in 225 here, it's going to stay positive. Keep track of the things that we found. That's equal to 0 pounds. Okay. If you don't feel comfortable looking at a structure and saying that's a zero force member, the math will always back it out for you, right? It's not a prereq. When I took statics in undergrad, my professor was roughly 1,000 years old, and he looked like a baseball glove. All right. He was super, super tan and super like looked like tanned cowhide. Okay. And he had this thing where he would bring in like this rubber, I don't know, it had to have been an eraser, but it was like, 2 feet long. And he'd be like, hey, yeah, it's a moment. Hey, see it? You see it? And I would sit there with my friends. I'd be like, I have no idea what this man is talking about. I do not see any of the things that he is talking to me about. And he'd be like, yeah, you just point at a truss. He'd be like, those are zero force members. So I'm like, I don't know how you determine that. We'll talk about it in a second, but I guess my point is understanding where the zero force members are is helpful and speeds up the process, but is not necessary for the process. Okay. Okay. All right. So now we've got, let's mark it on let's mark it up here. Maybe, there we go. We've got this force, we've got this force, we've got this force, and we got that force. We need to get two more. Now we're going to go to point D, right? Because if I go to point D, or we need one more, right? So I can either go to A or D, it doesn't really matter. I'm going to go to D, and then I'm going to use joint A to check and make sure that because I should be able to back out my reaction and it should equal the reaction force that I calculated originally. And then I will know that I have done some of this correctly. All right. So we're at joint D now. Okay, same deal as usual, right? Sum the forces in the x direction is equal to 0 is negative 450. It's still going to the left. Minus the x component of FDA. A cosine, no, that's sine in this case because of where the angle is. Remember this angle right there? Not that it matters because it's 45 degrees, but it does matter because using the correct trig function indicates whether or not you understand what you're doing in this case, right? And I would argue that understanding what you're doing is probably pretty important. There's no component there from the other one. We know everything in here, right? So we can just solve this directly. We don't even need the other equation. Sorry, let me do it this way. 450. We're looking for FDA minus FDC sine 45 is equal to negative FDA sine 45 degrees. So FDA is equal to FDC sine 45 degrees minus 450 divided by sine of 45 degrees. We plug in our stuff and we should get, negative 318.2 pounds in compression. So we know this one's compression, right? You can check it with the y direction equation. It should come out to the same thing, right? And it does. I will write this as like this. I would report it that way. We know it's in compression. We don't need to include the negative sign. Negative sign is kind of meaningless in reporting the results if you're going to report tension and compression. Why would you report it as tension or compression instead of using the negative sign? It's a good question. The reason is very much because some people might use the opposite convention that you use. And so you could have assumed that positive was compression. And if I just leave them as positive and negative, then that person thinks that it's opposite of what it should be. And then you end up building a truss that's good for not the loading that you wanted to load it for. Why would you use, it's the same analogy as why when you're doing problems, you cannot just ignore the units that the other people are doing, right? Everybody needs to talk about it. All right, the last thing is we'll check it, okay? And you can use, like I said, you can use joint A, or you can use sum of the forces in the y direction. Is equal to 0 is negative FDA cosine 45 degrees minus FDC cosine 45 degrees. The cosines are going to cancel, right? So you end up with FDA is equal to negative FDC, which is what we got. Good for us, right? That's what we want. We want to make sure when we have the opportunity to check, we should definitely check, right? We will do more of these next week because next class, there's kind of a thing. There's a thing going on. I don't know if you heard about it or not. Next week, we will do more. More method of joints. The key here is, I think, well, I told you guys we'd have 45 minutes of review, and we do. So next time we'll talk more about what zero force members look like. We'll do more problems, okay? And we'll just keep moving through trusses. All right. You guys have any questions? If you want to do an extra check, use point A and see, knowing the forces that you have in AD and AB, if you can get the reaction force back out. Okay? Because if you can do that, then it's done. Like you have full confidence. Okay. Mhm. Mhm. Yes.
Well, I thought that FTC was opposite.
So it is negative here, right? But remember, when we're reporting it this way, that's the magnitude, right? So we're using scalar equations. And so the negative sign is only to tell us in the result whether or not our initial assumption of direction was correct. It's not reporting that. So that's why redrawing the FBDs is important, right? So if you were going to draw an FBD for A, it's a good question. We'll talk about it right now. If you're going to draw the FBD for point A, right, you would have this force here, right? But we found that this guy was in compression. So now it looks like this. We have a tension and a compression, right? And then you do your analysis of point A with this directionality. Okay. So anytime you solve a joint, if you find out that it needs to be in compression instead of tension, the next joint where you see that force, flip it. Okay. Draw it the way, because now you have knowledge of it. When we don't have knowledge of it, we assume tension just because that's the standard convention. You can certainly do everything assuming compression. That's fine too. But your answers will look slightly different than what mine do. Just heads up. All right. I only had 2 people tell me about problems that they wanted to do for the review. So we'll do as much as we can. All right. Maybe. Nope. No, I'm good with my long distance provider. Thank you. We're not going to do those right now. It's fine. Okay. Cover that next time, right? Right now, the review for quiz. Topic 1. What are the things that we needed to learn from topic 1? Define mechanics as it applies to engineering, discuss applications of engineering mechanics, perform unit conversions, apply vector operations to force vectors, and compare and contrast vectors and scalars. Right, hopefully we feel pretty confident with the topic 1 stuff. We'll talk, most of the 2 questions that I got have little to do with unit conversions, and it's mostly to do with vector analysis. And so we'll kind of focus on that. Topic 2, identify equilibrium conditions, create free body diagrams for particles, and apply equilibrium analysis for to 3-dimensional systems. All right. Okay. So let's get into it. This was a problem that somebody posted up there, right? What I've got is, so I've got all these distances that are given to me in the learning goal part, right? And I've got this system that has a strut and 2 cables that are holding up a weight, all going through point C, right? And so a weight of 145 pounds acts at C on the strut. We want to find the magnitude of the tension in cable AC. Okay. Then part B is we want to know what the weight of an unknown hanging mass would be when the compressive force in the strut is 695 pounds. Then we're changing this up to what our knowns and unknowns are, right? And then the final one is we want to find the maximum weight that the cable strut system can support if the magnitude of the compressive force in the strut cannot exceed 1,100 pounds and the magnitude of the tension in the cables cannot exceed 300 pounds. So a lot to unpack in that one, and it seems like it's a lot harder than it actually is. But we're going to get started first with free body diagram, right? So remember, part A is we're trying to find the force CB, right? Or sorry, the magnitude of the tension in cable AC. We want to know the cable tension. Great. Let's do this. So we'll start with our FBD. In this case, we are going to just have one for point C. And then we will put our I believe that's our sense of our rotations here. There we go. Okay. So I've got some weight in this direction. I'm going to have the force CB here. Notice I am assuming that it is in tension to start with, and then I'll have my 2 cables, right? This one's going to be FCD on the top, and this one's FCA. Okay. Important things to note here are that this drops straight down to the ground, right? FCB, here's point B. Point B lies on the y-axis, right? It is given to us. Point A is going to be somewhere over here. Point D is in line with point A on the x-axis, right? So here's our x-axis, positive that way, and Z is positive upward, right? And I think that covers all of our points. The next thing that we need to do is show our distances. This is the distance B from here to here is our distance A. From here to here is distance D, and from here to here is the distance E. All the way up from the y-axis to C is the distance C. Those are all given. I'll write them down over here. So what do I know? That A is 7.5 feet. B is 4.7 feet. C is 9.3 feet. D is 3.5 feet. And E is also, it's 4.5 feet. What else do we know? Well, in this case, for part A, we know that the weight is 145 pound, right? But specifically, if we're going to write it as a vector, which we should, it's negative 145K. Pointed straight down. And for this one, we want to find the tension in the cable AC, right? So FCA or FAC, however you want to write it. Okay, I've got a three-dimensional problem. I've got nothing but distances. What should I be looking to do immediately? What should that trigger in my brain? Unit vectors, exactly. Right? Especially since we've got a strut, which can be modeled as a short link, and two cables, which means that all of my forces have to be pointed along those directions, right? So we can start, if I want the unit vector for CA, right? That's the distance CA divided by the magnitude for CA. Okay, so if I'm going from C to A, I need to go what? Well, I need to go D distance in the X, right? Because I'm at C and I'm coming down to A, right? So go there. So I need to go 3.5 I. I would need to go negative A plus B in the Y direction, right? Because I'd have to go back this way. That's negative A plus negative. The negative, the quantity A plus B. So minus 12.2 in the J and minus 9.3 in the K. Just drop it straight down. The magnitude of that, if I do the square root of the sum of the squares of this vector, is what? 15.73, very obviously without need of a calculator. Okay, and I'm just going to leave that. You know what? I'm not just going to leave that. That's gross. So I'm going to divide it out. Right? We get 0.22 I minus 0.78 J minus 0.59 K. And that's the unit vector CA. Here's a question, just for funsies. What if I said, you know what? I want the unit vector from A to C. How does that change the unit vector from C to A? Okay, let me ask you this question. How do you go home from here? Yeah, you go just the negative direction that you traveled to get here. So if I wanted to travel in the opposite direction, I would just multiply this by -1. All right. Great. Rinse and repeat for the other two, right? So UCB is RCB, no, not the magnitude, divided by the magnitude of RCB, right? So if we do that, we're going to get, well, if I want to go from C to B, which is right there, right? I forgot to label it earlier, but there it is. I want to go from C to B. In the X direction, I don't have any travel, so that's 0, right? Doesn't travel anywhere in the X. I have to go backwards by B, so minus 4.7 in the J, minus 9.3 in the K. If I take the magnitude of this, 0 squared plus 4.7 squared plus 9.3 squared square root, carry the 2, gives me 10.42, which simplifies to 0I minus 0.45J minus 0.89K. And there's no units because it's a unit vector, right? So that's kind of the whole point of the unit vector, is that it gives us a normalized or non-unit version of what we're looking at. Okay. Fantastic. One more. UCD. And UCD is, you guessed it, the magnitude, or RCD divided by the magnitude of RCD. In this case, well, we need to go negative E in the x direction, so minus 4.5 I. But the rest of it should look like how we got to A. Our magnitude is not going to be exactly the same, but we should expect it pretty similar to UCA, right? Because 4.5 and 3.5, how big of a change does that actually make between our magnitudes, right? So 4.5 squared plus 12.2 squared plus 9.3 squared square root gives us 15.99. So UCD is equal to negative 0.28 I minus 0.76 J. Notice it's pretty similar, right? We're pretty close in all of these. Minus 0.58 in the K. Okay. I'm going to save, for the interest of space, I'm only going to save the result of these up here. Okay. Any questions on how we find the unit vectors? No, not hearing anything? We're okay with how, we're good with those. We're good with unit vectors, right? So what do we do with the unit vectors? Well, now I have a vector. If I multiply that by the force magnitude, I get a force vector in the direction of the unit vector, right? Which is what we want. So let's start doing that, right? Let's build our force vectors. Okay, so force CA is going to be equal to 0.22, the magnitude of FCA in the I, minus 0.78 times the magnitude of FCA in the J, minus 0.59 magnitude of FCA in the K, right? FCB is 0 in the I, minus 0.545 FCB in the J, minus 0.89, bless you, FCB in the K, and FCD is equal to negative 0.28 FCDI minus 0.76 FCDJ minus 0.58 FCD in the K. And we have our W vector, but just to remind us, right? All of these vectors would be in pounds when we report them, all right? So we've got all of our vectors. Fantastic. How many unknowns do I have? Well, I have 3 unknowns, so I need to use 3 equations to find them. It seems like to me that the easiest equation to use to find these would be some of the forces X, Y, and Z. So let's start there. Okay. If I take some of the forces in the X direction, I'm going to take all of my I components and put them together, right? So that's 0.22 FCA minus 0 or plus 0, whatever you want to say, minus 0.28 FCD. equation 1, right? Sum of the forces in the y is equal to 0. Now I'm going to take all my j components right here. Minus 0.78 FCA minus 0.45 FCB minus 0.76 FCD. And then finally, sum of the forces in the z direction. Label it 2. Minus 0.59 FCA minus 0.89 FCB minus 0.58 FCD minus 145 for our weight. Don't forget the weight. That's equation 3. There is no way for us to solve any one of these equations directly for any quantity. So we are going to have to do the long method of substituting in and out of the equations to try to solve things, right? That's where we're at. So I'm going to erase my force vectors for right now, since we already have them over here, and we don't really need them for anything right now. Yes, exactly. Okay. So I'm going to start with equation 1. Why? Because it only has 2 things in it, and I can solve for one of them in terms of the other, right? So does it matter which one you start with? Not really. Why would I pick that one as opposed to any other one? Because it only has 2 things in it. And it gives me a clear relationship. Does it matter if you solve for CA or CD? No, it doesn't. But the way that I did it and the way that my brain functions is I solved for FCA, which is going to be 0.28 divided by 0.22, which happens to be 1.27 FCD. Does everybody see where I pulled that from and the algebra that I did to get from here to over here? Do you want me to step through it? Anybody? No. 0.22 FCA minus 0.28 FCD is 0. When I move 0.28 over, it becomes positive. Divide by 0.22 gets me 1.27. Now, everybody's favorite part. I have to take this expression, and I have to carry this through into another equation. So the way that I did it was I took that and I plugged it into equation 2, because there's really no good spot to plug it in. So way that I progressed was I started with 1, I moved to 2, and then I solved for something in 3, and then I went back and solved the other ones. Okay. So first things first, let's plug what we just found out into equation 2. So just to highlight it, we're going to take this and we're going to put it in there. If we do that, we get 0 is equal to negative 0.78 times FCA. Well, FCA is 1.27 FCD minus 0.45 FCB minus 0.76 FCD. So what we're going to do is we're going to solve for FCB here. So if I pull my 0.45 FCB over here, if I multiply 0.78 times 1.27, right, I get negative 1. Hold on a second. That doesn't make sense to me. Oh, and I add it. All right, so I'm doing all this together. I'm going to take all this, multiply it together, and then subtract 0.76. Those are both negative. They stay negative. It's negative 1.75 FCD. Right, and so what we find out is that if we go to solve this, I divide by 0.45. I end up with the expression FCB is equal to negative 3.89 FCD. Guess what? Take that and we put that in there. And we also put this in here. And now we have a mega expression that we can solve for FCD, right? Super, super fun. Super fun. I maintain not difficult, but tedious, time consuming, right? All predicated on the fact that we need to understand that we need a unit vector to define the direction of our force vector, right? Because we're trying to solve for the magnitude of those force vectors, right? Yeah. I would recommend doing the work out because if you fat finger it and the answer comes out wrong, I have nothing to give you partial credit for. If you just write an answer down and it's wrong, you've forced me to give you a 0. Right? Facts. I can't grade stuff that's not on the paper. It's probably not the best. Probably not the best choice. So I'm gonna delete that and move this up here. Okay, so we're gonna put both of those into equation 3 now, right? And that's fun. So we end up, I'm going to move the 145 over to the left-hand side, and that is equal to negative 0.59 times FCA. But we know that FCA is 1.27 times FCD, right? Minus 0.89 times negative 3.89 FCD. We know that from the red equation that we just had. We're subbing in for FCB. Minus 0.58 FCD. Okay. You multiply. You just multiply all the things and then you just subtract them all. Right? That's seems simple enough, right? Maybe. The page doesn't turn. Where am I? Oh, I'm in the wrong part of the problem. There we go. All right. So what we end up seeing is that 145. Did I mess something up? But is there a not a negative there? Oh, this ends up becoming positive right here, right? Because it's a negative 0.89 times a negative, right? So this is going to end up being positive for us. So we get 145 is equal to 2.13 FCD. FCD gives us 68.05 pounds. But we weren't asked to find FCD. But also, I want you to notice that that came out positive, which means it's actually in tension, like we drew it, right? That's important because it's a cable and it has to be in tension. So if you found out that that was negative, right, you would know that that's a problem with your answer, okay? Hopefully you would know. FCD, 68 pounds. Okay. Well, now, look, I don't have to go back and solve 1 and 2. I already have expressions for my other 2 in terms of FCD. So now it's just plugging this in here and in here to find FCA and FCB. FCB is negative 3.89 times 68.05, which apparently I decided not to calculate at all here. I mean, it doesn't really matter. We weren't asked for it, but I'm going to do it anyway right now. Negative 3.89 times 68.05. Negative 264.7. So we'll just call it negative 264. Negative 265. We'll round it correctly. I want you to notice that that came out as negative. That indicates that we chose poorly, and FCB is actually in compression, which is fine because it is a metal link. It is not a rope. Great. Also plays into the next part of our problem, which we will talk about in a second. And then finally, the answer that we were asked for is FCA, which is 1.27 times 68.05, or 86 pounds. And there we have it. Wonderful. Fantastic. All is well. So, questions on that part of the problem? Yeah, Colin. Yep. You got to isolate one variable, solve for that variable, and then you go back and you plug that variable in to get the other two forces. Okay. All right, so the next one, the next part of this was, now we're going to change this. I know what the force is in the link, right? And on top of that, I was told in the problem statement that that is a compressive force, right? So that's going to change our FBD somewhat. It's going to change our equations too a little bit, right? So I'm going to get rid of these equations. We'll have to have a new set of equations for this. And we don't know W anymore, right? So we have to get rid of that because we're trying to find W. Yeah. Mhm.
With that, why does that change our equation?
What do you mean?
Like, we use the vector.
With the unit vectors, the fact that we use unit vectors doesn't change them. What changes them is that the forces are different now.
Yeah. Abstract, I guess, calculation, just plug in our other group. Not really what's overall inside of it.
Yes and no, and there's a reason why in a second. We'll go through it. There's a important difference that's going to change one of them. And that difference is this. This is in compression now, right? Or FBC. So I'm going to erase these forces. And our new knowns here, we don't know the weight anymore, but we know FBC, right? Well, we know the magnitude of FBC is equal to, what was it, 695 pounds. And we were told specifically that that is in compression. And that is important because it flips the sense of our vector, right? Which means that we're not really talking about this unit vector anymore, talking about this unit vector. Okay. W is still acting directly in the K direction, right? But we just don't know what W is. So we have to solve for it. We also don't know what FCD and FCA are because the last time when we just solved this, we had 265 pounds instead of 695. So that's going to change the tensions in the cables as well, right? So we still have three unknowns. We're still going to have to do similar amount of equations. You can basically, and yes, Ryan, so your question, you can basically keep most of the things that you just did, which makes this a much faster process. Like the FCA is still equal to 1.27 times FCD, right? Where it changes things is specifically in equations 2 and 3, right? And it actually, it's going to allow us to solve a couple of things pretty quickly right off the bat, right? So we don't necessarily need to build out our force vectors again, right? You guys already have them written down. You can go back in the video and watch them. But the whole point is the way that these problems are set up, if you had done it symbolically to a point, this becomes a lot easier and we don't have to repeat all of our work again, right? So things that we already know, right? If I sum the forces in the x direction, just do it. If I sum the forces in the x direction, set that equal to 0, I'm going to end up with FCA is equal to 1.27 FCD, right? The x direction forces don't change because CA and CD didn't change, right? UCA and UCD didn't change. What is going to change are the next two equations because we had to change the sense of the CB vector. Okay. And does everybody understand why I flipped this? This is the key to doing this, right? If you don't flip it, it's still in tension. Because we were told it's in compression, it needs to be pointing the other way, right? How do we point it the other way? You multiply the unit vector by -1 and you move forward, okay? Okay. So equation 1 stays the same. Some of the forces in the y is going to change a little bit. That's going to be -0.28 FCD. What am I doing? I don't know. I'm not looking at the right thing. Hold on. Sorry. It's too many things. All right. So first thing we're going to do is we're going to calculate the FCB portion. So 0.45 times 695 is 312. 0.75, right? Minus 0.78 FCA. Minus 0.76 FCD. And then sum of the forces in the z direction is going to be 618.55 minus 0.59 FCA minus 0.58 FCD minus W. Okay. So again, very similar to the other three equations we had, just plugging in the things that we know differently, right? To start off with, right? Let's see. Where do we want to go first? Okay, so we're going to plug equation 1 into 2, right? Same thing that we did last time. And we get 312.75 is equal to 0.78 times 1.27 FCD minus 0.76 FCD. So because of the difference in what we know and what we don't know, we can solve for FCD right away, right? And FCD becomes 178, or we'll call it 179 pounds. Okay, still in tension, so that's great. We can go back and get FCA immediately, right? So let's do that. FCA is 1.27 times 179, which gives us 227 pounds. Okay. And then finally, we just plug those numbers right into FZ, right? So we get that the weight is equal to 618.55 minus 0.59 times 227 minus 0.58 times 179, giving us a weight of 380.99, or just 381. Let's just call it 381. Be done with it. 381 pounds. All right. Much faster than the first one, right? Change what we know, plug in as we go. The last one's even faster because we don't have to change our FBD at all. We can just use the equations that we set up to kind of go after it all at once, right? So what are we looking for in part C? We're looking for the maximum weight that we can hold given some conditions. I know that the maximum force in the strut can be 1,100 pounds and the maximum tension in my cables can be 300 pounds. So I set FCA, CD to 300 pounds, and I set FCB to 1,100 pounds. And guess what? We just solve equation 3 right there. We solve FZ, right? Because when we originally wrote F sub Z, some of the forces in the Z was F was FCB times the unit vector there, so 0.89 minus FCA times 0.59 minus FCD times 0.58 minus W is equal to 0. We have all of these. 1,100 times 0.89 minus 300 times 0.59 minus 300 times 0.58 is equal to the weight. Turns out that if you crunch all of those numbers, the weight is equal to 628 pounds, roughly. Done. Really good example of keeping your stuff symbolic until it's time to plug in, right? If we had only saved this, right? We'd only saved this sort of thing here. You know, that's great for FCA, FCD, but because I didn't include how we changed FCB in there, that kind of throws something in the punch bowl, right? Okay. Any questions regarding this in particular? Big takeaways. Unit vectors, systematically solve your equations. I'm going to urge you to make sure you write down as much work as you can on the paper. Okay? Because the difference between you showing me and I'll be like, oh, look, sign error, -1, move on. Did you get the right answer based on that sign error? Sure. You don't get penalized for it. Again, the sign error was the issue. The difference between -1 point and I didn't write any of these things and just saying the weight is 500 pounds. If it's wrong, it's wrong. You're forcing a binary situation. Magic answers. So I want you guys to understand this. I want to be very clear about this. The point of you guys doing these classes, I know it feels like, is to get the right answer. Okay? Getting the right answer is not the point. Understanding how to do the problem is the point. Show me that you understand how to do the problem. Okay? Show me that you understand the process. Answers are, in the real world, answers are open-ended and come in many solutions per problem type. They are not defined, right? Don't focus so much on the answer, focus on the how. How did I get to that answer? The other part of that is that at some point, somebody is going to ask you, well, how did you come to that conclusion? And if you said, well, I put it in my calculator and that's the number I got out, that doesn't hold as much credence as saying, well, let me walk you through my solution process. Okay? We obviously do not have time for this problem, but I will show it to you and you guys can access it in the discussion question, right? This one is to determine the magnitude of F2 so that the resultant force is directed along the positive U axis and has a magnitude of 50 pounds, right? So I would say, tip for this one, think about how we project a vector onto a different axis, right? Think about how we would project a vector onto a different axis, okay? And also another tip would be assess whether or not you have right triangles. Okay, those are my 2 hints for this one. Okay. And what do you do if you don't have a right triangle? I would recommend. Give up. Don't give up. Don't ever give up. Only you can prevent forest fires, etc. Okay. Yep. Okay. Since this is the last real class for the day, for the week, the day. Yeah, for the day. Sure. That works too. For me at least. You guys might have another one. If you are studying over the next tonight and tomorrow and you have a question, please reach out. I would like to help you, but I can't help you if you don't let me know that you need help. Okay. Next week, we will continue with this. Remember, Monday is a holiday. Please don't come to class on Monday. No one will be here. You'll be very sad that you drove here. If you are not feeling in the greens, please come see me. I would love to talk to you about it.